Good afternoon and welcome, folks, to another one of our virtual tours of outer space. My name is Josh. I'm part of the Morrison Planetarium team at the California Academy of Sciences, and we are sending from our homes to yours to check out our solar system and beyond. So I get to be the pilot of our spaceship of the imagination. I don't want to use that term, actually. It's probably copyright. We are going to be checking out some of the stuff that exists around us in the universe, and if you have an idea about where we should be checking out, a suggestion, if you will, by all means, throw it in the comments, the chat up on the side. We are monitoring. My producer, Mary, is watching. And if there's someplace that we think we can manage squeezing in, we will happily do so. So the software we are using to check all of this out is OpenSpace. OpenSpace is a very cool thing for you to use. And it is planetarium software, but it's planetarium software you can use at home. Case in point, I'm at my home flying around planet Earth. So if this is something you think is really cool, we would encourage you to download it. It's the OpenSpaceProject.com, and that's where you can find the software itself. If you need assistance with using it, there are forums, there's a Slack channel, I believe, all sorts of great resources for you to figure out how to make this something that you can use to observe the universe. I saw a question, ISS above is asking to see the ISS. That seems a little on brand, but also a manageable request. Let's go check out the ISS. Notice this fun orange orbit flying around our planet. That is, in fact, the International Space Station, ISS to her friends. When we're heading down to the ISS, it's really going to seem like the International Space Station is not moving, like it's kind of hovering in space. Well, that's kind of the case, but it is actually moving very quickly with a frame of reference of the Earth. How fast? About 17,000 miles an hour. It's zooming around our planet once every 90 minutes. So it is, astronauts on board, I would say, are some of the fastest moving humans at any given moment. You can almost imagine some of the astronauts on board, too. If we get close enough, this is a really good texture. I should visit the ISS more often. You can see all sorts of cool bits and bobs on the surface of the ISS, but you can also start to see some of the parts that are adapted to interface with human beings. Stuff like doors, stuff like the capsules, the Soyuz that they use to get to the ISS and back. We might even have a Dragon capsule or two hanging out somewhere on here. But as we look around the ISS, that gives you that little bit of human scale, which I think is something so fascinating in a show like this, where we are fundamentally dealing with an astronomical scale, something that is kind of incompatible with a human scale. But as you look around on here, you'll notice that from side to side, edge to edge, if you were to count it out, the entire ISS is about the same size as a football field. That is a pretty big object, to be sure. Not all of it is where human beings walk around. For example, you would definitely need a spacesuit to interact with most of the extent of the ISS. The solar panels, for example, are not a place that you just get to go out and hang out for your lunch break. The interior parts are a little bit more restrictive, but I'm a big fan of virtual reality environments, and there's a really cool NASA tool that lets you explore the ISS in VR from inside the ISS, and I am fascinated with it. So I don't want to spend the whole show so close to home. We had folks mentioning that the ISS is going to be in sunrise 24 minutes from now. That would probably be the case if I were using an accurate timestamp, but I ran us back a day. So this is where the ISS was yesterday at 34 minutes past 0 on GMT. So when we're looking at the International Space Station, zooming around our planet, you can actually see right where it's about to pass over. If I were to extend that little trajectory out, I would say it was passing over France, maybe Germany, in just a few minutes from the moment we are seeing it. That is always a super cool thing to see. So zooming away from there, let's see if we have other suggestions on where we might go. If not, I've got a hankering for the moon. So I'm going to take us there in the meantime. But if you've got a non-moon suggestion, by all means, throw it in the chat. We are monitoring. So zooming in, we are going to check out the moon because I think the moon is just a fantastic object. There are so many cool things to see. And these days, the moon is getting harder and harder for me to spot on our morning walks because we are past our third quarter moon. We are in its waning phase, moving probably at a crescent right about now, but getting smaller all the time. We can actually see it where it was yesterday, where a little bit of the moon is lit up. But let's try this out. If we go into our controls, we can actually change it so that there is no nighttime on the moon, and we get to see what would normally only be visible during kind of a full moon. Right about here. Should be lined up right about with Earth. Rob wants to know if the dark side of the moon were illuminated, would it look much different than the normally visible side? Are there images of this in OpenSpace? Boy, Rob, you set me up perfectly. Thank you so much. Your check is in the mail. But when we look at the moon from the side we're used to seeing it, what we call the near side of Earth, this is what it looks like. Now, I love looking at the moon in pop depictions, in music videos, and TV shows. Wherever the moon appears, I like looking for a couple certain features. You should be able to spot right down here the Sea of Serenity and Tranquility. That's two about equal-sized globules of dark material right here. There's one at the top, one at the bottom, and then two more darker regions kind of in parallel down here, one on the left, one on the right. So if you can spot this structure, it's usually a pretty good depiction of the moon and a great way to tell that you are looking at the side of the moon we are familiar with seeing. If you focus too much on the light stuff, generally it's just lots and lots of craters, and you have to be very practiced in lunar features to be able to recognize one group of craters from another. So let's say this is our near side. Take a mental snapshot of what this looks like, and then I'm going to fly us over to the far side, over here. I bet instantly you can tell this is different. Now, there is kind of a funny little artifact here. It looks like someone took a razor blade to the side of the moon and split it open. That's where the map of our moon does not quite fold perfectly. There's a tiny little gap there where you can see that this is, in fact, a digital artifact. But let's not pay too much attention to that. Let's focus on all the really cool stuff. There are a few dark areas over here, but I think that's the Sea of Moscow, the Muscovy Sea. And there aren't too many others. Turns out the far side of the moon is pretty much dark region free. There's just not as much evidence of that kind of movement over here. This is the sort of crater-filled ancient side of the moon, where when we look on the other side, we can see some more recent change. There's a lot more going on the near side. So our moon looks very different near side to far side, and you can explore that in OpenSpace. But I'm going to do you one better. You asked if there were cool images of the near side and the far side. And as you've seen, we can see it. So you could call that an image. But I would really call these models. And what's the difference? Well, these are very three-dimensional. If we drop down onto the surface, you can actually start to see some of that height, some of that change in relief. This is a 3D surface with mountains and valleys, craters, rills, all sorts of wonderful features. So I would encourage you to look at it. Absolutely. Look at it from above, but don't just stay above. Move around, drop in, change your angle, jostle things around, and you will be amazed at discovering how much cool stuff is going on here. Okay, so we have a bunch of questions popping up, and I'm seeing a little bit of a focus on Galilean moons. Twist my arm. I will always go visit Galilean moons. Let's go see what's happening out there. So, why does Io have ice on it like the other Galilean moons do? So that is a great question. There's an ongoing debate amongst me and my astronomy friends of if it's Io or Io. I think both are probably well supported. I would say Io might be closer to the Greek. Io is what most astronomers like saying today, but that's a interesting point, one that I need to research further. When we check out Io, I'm just going to call it for now, does it have ice on the surface? My recollection is that there are definitely icy surface deposits on Io, if for no other reason than there are some volatiles and it's a cold place. I don't know if there's ice to the extent that like Europa has, but there's probably some icy regions on the surface. Most of the activity that's happening on Io is actually happening in Io. So there are also volcanically active regions, places where rock flows onto the surface and then freezes into solid rock. So inside Io, there's probably a lot of activity, a lot of heat, a lot of motion. On the surface of Io, things are probably still, frozen. So if there's any liquid on the surface of Io, I would be inclined to say that it's ice. And over here, you can see a lot of bright white deposits. If I had to guess where there might be ice on Io, I would say around those because I believe they're probably close to polar regions, and that is a pretty good bet on most systems that that's going to be a chilly place. And not quite polar, but still kind of closer to the poles than the equator. Okay, so Io, super cool. Since we were talking about ice in Galilean moons, I feel the compulsion to stop by Europa, just because Europa is so awesome. We are approaching Europa from the distant from the sun side, which always makes things a little challenging, not to slam into it, but I can see that big dark circle getting bigger, and that tells me we are at Europa. So Europa, about the same size as Earth's moon, give or take. The surface could not be more different than Io, though, where you saw tons and tons of craters and volcanoes and color variation. Europa is much more uniform in color. Now, in some images, you can really see some dark, kind of brownish dun regions popping out. I believe those are places where some clay-like deposits have been brought up to the surface, and that is just an amazing thing. To see that much activity, that much motion inside an icy moon is proof that there is something going on in there. We had a presentation from a Europa expert a while ago telling us all about the interesting features you can see and how the surface changes. I would be doing his expertise a disservice if I tried to relay all of it to you secondhand. I would say go check out the video on our Cosmic Conversations. I believe that was Mikey's. But if you ever see a scalloped feature, now it kind of looks like pinking shears if you ever took them across the surface of Europa, but sort of a very regular wiggly line. That is where we are seeing a tidal interaction between Europa and Jupiter, where Jupiter is tugging on Europa and breaking the ice in kind of a rhythmic, organized way. That is just super cool. So if you get a chance, download OpenSpace, fly around, look for a feature that kind of has that delicate scalloped edge. I think I see one right up here. Yes! Check out these wiggly lines. I'm trying to center them as much as possible, where it sort of looks like crescents repeating over and over again. I'll try and point at it with my mouse. 1, 2, 3, 4. That is that kind of tidal interaction where something is breaking repeatedly as Jupiter pulls on Europa unequally. Okay. Man, Europa. Is there a moon in an orbit between Io and Europa? I'd be willing to bet there are, because these are the Galilean moons and absolutely big moons that we can see from Earth. That's why we've known about them for a very, very long time. When we look at the minor moons of Jupiter, there are tons of them, and many of them happen to be oriented to that kind of elliptical plane where the Galilean moons hang out. If there was something there, I would say it would have to be a very small moon, because if there was a big moon, it probably would have been disrupted. I know most of the minor moons hang out a bit farther out, so I'm actually going to second guess myself and say there probably isn't much hanging out directly between the big Galilean moons. But I can see Mary typing away furiously. I bet she's going to have an answer for us shortly. When we're looking at all these Galilean moons, I'm going to bring their orbits up so you can see where they are hanging out. And then let's see if I can bring up some of our more minor moons and see if there's a way for us to show what's going on here. So I'm going to check out the planets of the solar system, Jupiter, and its moons. I only have the Galilean ones loaded up. So there are tons of minor moons of Jupiter. If you brought them up, we'd actually be able to see if there's any that pass between Europa and Io. So I will say that that is a definitely answerable question, but not answerable by me at this current moment. Let's see. Where else has cool stuff handing out? Especially oriented to moons. We've been doing great moon stuff so far, and moons are my favorite. I'm going to head to another one of the moons that I really enjoy in our solar system. I'm going to head out to Phobos. Now, Phobos is one of the 2 moons of Mars, and it's actually one of the spots, surprisingly enough, that has been considered as a base. Now, that would be a big challenge. We've not built a moon base on our own moon. So the idea of building one on Phobos is still kind of science fiction-y. But there would be some big advantages. We are pretty sure that inside Phobos, there's a whole bunch of ice. It's got this weird ovoid shape. It's definitely not a big round moon. It's kind of a squashed, funny-looking moon. But when we're talking about Phobos, we actually, let's see if I can get a better image on there. There we go. Now this one's still all smoothed out. Let's try this. There we go. There's the lumpy Phobos we all love. So when you look at lumpy Phobos, this is a very low density moon. What I mean by that is that when you take the amount of weight it has, the mass it has, and divide it by the amount of space it takes up, it's a pretty low number. So this is the kind of moon that rather than being made of like lead or rock, you could imagine it being made of like pumice. It's light. One of the models, one of the explanations for why it's so light is that it could be a significant amount of ice. If that were the case, then Phobos would be a great refueling stop for people that are heading to Mars. Having a huge amount of ice in orbit around Mars could be a place where you would restock on hydrogen and on oxygen, the two components of ice water, before you headed back to Earth. That would be super convenient, and blasting off from the surface of Phobos is easy. Turns out, as the mass of an object goes down, the ease of getting away from it goes up. It's a lot easier to escape Pluto than a black hole. So when we're talking about something like Phobos, the escape velocity is very low. In fact, so low, one of my favorite factoids about it is that if you were on a bicycle on Phobos and you got going really fast and hit a ramp, you would probably reach escape velocity and could blast off. That, to me, sounds absolutely, if for no other reason, that it makes the flight scene in E.T. look semi-plausible. Okay, so talking about Phobos and the potential for human beings exploring beyond planet Earth, I think is a super cool opportunity, if for no other reason than human beings going out and visiting other worlds, other moons, is wonderful parts of science fiction. I like the idea of human beings exploring, checking stuff out. Roger wants to know, how large is Phobos? I think it's small. I would say a couple miles across. It is definitely not going to be anywhere close to the size of our moon, and you can actually tell a great deal about the size of it based on its shape. A moon that is big and low density like this would probably have made itself around. Something that's small and lumpy like this, 7 miles, boom! I'm relatively close with my wild guesses. When we're talking about something like this, something sufficiently massive would have made itself more round. Because it is so bumpy and lumpy and irregularly shaped, we are pretty confident saying that this is a small object. And that test runs true for many objects. Last week on our Cosmic Conversations, we were talking about some of the asteroids and comets of our solar system, and we had a wonderful case in point talking about Vesta, I believe, is round from some angles. So it's right at the cusp of what should be a round object. When you go to smaller objects like Cleopatra, the comet spelled with a K, then you're talking about things that are very irregular in shape. Even something Bennu-sized, which is large but not miles across large, is irregularly shaped. I should say regularly shaped but not round. So yes, Roger wants to know, is it larger and closer than the other one? Phobos is the bigger moon and closer to Mars, so it has a shorter period. When you talk about the other moon, it's a longer period. That's Deimos. Deimos does take longer to go around. I believe for Phobos, though, it's only about 8 hours for one full rotation. So on Mars, I love thinking about this. A day is almost the same as ours. We call that a sol. For a month would be dramatically shorter than our own. If you were using Phobos to calculate your month, you would have a month of only 8 hours. And if you're doing years, it would be twice as long as an Earth year. So you would take your age on Earth and divide by 2. I would be, let's see, 16. That sounds awful, actually. Let's not do that. Backing up, any other solar system objects we would want to check out? Anything cool nearby or far away? Tell you what, I'm going to show you what is, I'm going to say this week, my favorite object. That's going to be kind of a superset of where we live. We're going to go check out the Milky Way because I think the Milky Way looks so cool. So when we're talking about the Milky Way, there's a couple things we can do right off the bat. First of all, the stars around us are part of the Milky Way. As a bad analogy, as grains of sand are to a sandbox, as cells in your body are to you, we are one tiny part of what makes up the Milky Way galaxy. So as we zoom back, you can start to see more and more stars. The stars are thickest in the disk of the galaxy, so that's where we'll see the most. Once we get kind of away from the disk, the star population thins out dramatically. And we can start to pull in this super cool 3D model of what we think our Milky Way looks like. Why do I say think? Well, because no one's ever taken a photo of the Milky Way like this. The farthest away we have sent our spacecraft is still very close to our own solar system. So trying to take a photo of the entire Milky Way is like trying to take a picture of North America from your car. It's really hard. Your car would have to be way above North America, and that doesn't bode well for you or your car. So when we're looking at the Milky Way galaxy, this is based on our measurements in a variety of different colors of light, trying to figure out where the stars and the dust are nearby, and comparing that to other galaxies we see to make sure we've got a good guess of the right shape, the right size, the right distribution. And lo and behold, this does seem to be a pretty good match. So we are super excited about a model like this. And if you really want to make a model at your house that's relatively accurate for the width of the galaxy as compared to its height, sort of, the thickness of that disk, and that central bulge right in the middle, I'm going to let you in on a secret DIY recipe. What you got to do is look around your house and find this rare object we all call physical media, or a compact disk. And if you can find a compact disk at your house, quite frankly, kudos to you. Good for you for holding on to archival technology. But if you have a disk, find a marble and jam it into the middle part of that CD, and all of a sudden you've got a very good model of the Milky Way. Turns out a model of the Milky Way should be about 1,000 times as wide as it is tall, and that's about true for a CD. And the disk part should be about 10 times the thickest part of the disk. No, it might be a little more than that. It might be closer to 30. But it turns out this marble in a CD is actually a really good measurement. And a CD, if I recall correctly, is about 5 inches across. So if you took that and you multiplied it out about 20 times its diameter, not including the dark matter ring around us, and you put another CD with a marble jammed in it, you'd have a great distance model of where we find the Andromeda Galaxy. The Andromeda Galaxy is the closest big galaxy to our own, but out here you can see an actual map of the distribution of galaxies. It's called the Tully dataset. Looks like somebody spilled Skittles all over in 3 dimensions. We're seeing color-coded density mapping to show us where the densest regions of the universe are. You can see around here there are some very dense regions not too far away. I see one of them. I'm going to bring up my mouse right here. I'd be willing to bet, just based on the distribution, that's the Virgo Supercluster. So the Virgo Supercluster is the densest, most happening part of the universe around us. My boss likes to say that if that is downtown San Francisco, the Virgo Supercluster is where all the cool, exciting stuff is happening, then we live in Colma. And as a person who lives in Colma and has been stuck in Colma for months and months and months, I'll say that's kind of true. When we zoom back even more, you can start to see that San Francisco might be the biggest city around, but it's not the biggest city overall. There are plenty of other gigantic superclusters in the universe farther away. As we get farther and farther out, we're bringing in some of the most distant galaxies human beings have ever mapped. This is the 2-degree field, the Sloan Digital Sky Survey. All sorts of cool deep sky stuff is coming in. So we are seeing galaxies that are many billions of light years distant. So light from these galaxies has taken billions of years to reach us. And if we go out even farther, we can see even more distant things than the most distant galaxies. These are quasars, bright hearts of baby galaxies just beginning to shine, much closer to the beginning of the universe than today. We had a question come in from Roger. If you can get a picture of the Milky Way by a reflection of it on another gravitational lens, such as one of the Magellanic Clouds. Woof, there's a lot to unpack there. If we had a uniform distribution of gas, maybe like a giant slab of gas out there in space, and we could very carefully look at the light from our galaxy reflecting off of it and calibrate it for the perturbations that exist between us and it, and the distance and the tilt. Maybe, but I would say that getting a picture of our galaxy bouncing off something would be a huge challenge. Number one, to collect enough light. That sounds difficult. And number two, to be able to kind of suss out the picture from it. That sounds really difficult too. But we have supercomputers. Maybe. I do know that we have seen some very interesting stuff in terms of reflections on a cosmological scale. We've actually seen the light from the same supernova bouncing off multiple galaxies. And that's a really cool thing to think about. That a supernova went off somewhere in space a while ago, a long time ago. Its light reached us here on Earth. And then we saw light bounce off a galaxy from that same supernova and reach us. And we saw light from another galaxy. Theoretically, in the future, will reach us too. So that's a really cool thing because it gives you kind of that 3-dimensional scale of the universe around us. Granted, between witnessing those bursts, we're talking about potentially thousands, tens of thousands, millions of years, but it is still possible that we would be seeing light from the same supernova bouncing around space. I think Roger's idea is that in the same way, we'll be able to see light from the Milky Way bouncing off a nearby galaxy like the Lesser Magellanic Cloud, and then be able to see what we look like. Potentially, But I would also caution that with something so close, it would be like holding a mirror up to your leg. You might not get a great whole body picture. You'd probably want the mirror to be a little farther away, and with distance comes a greater interval of time. So galaxies do change, but they change slowly. So if we were able to put something within, I don't know, a couple million light years, you might still get a pretty good picture. It's an interesting idea, Roger. I need to think about that one for a while. But we've got an expert coming up in a few weeks who might be a great person to ask. I will write that down and make sure that if you tune into Sophia's upcoming Cosmic Conversation, that we have a chance to ask her that exact question, because that sounds absolutely fascinating. I'm taking us back to Phobos, not Earth. But I think we are approaching the end of our conversation, so I would like to thank all of you for tuning in. But there is something I have to ask. If you have enjoyed these programs, if you are enjoying the broadcasts we do here through OpenSpace, there is a survey that the good folks at OpenSpace would love for you to take. OpenSpace is a NASA-funded project. We want to tell NASA how amazing this product is. So if you have the opportunity, we will drop a link in the comments. Please take the survey. Let us know what you think. And the first set of respondents get their very own NASA meatball sticker mailed out to them. So thank you so much for participating in all of these broadcasts. Thank you for sending us the wonderful questions and suggestions of all the cool places to visit. On behalf of myself and Morrison Planetarium and OpenSpace, thank you all for joining us, and have a wonderful